Hi guys, welcome to another video from the series about statistical sampling, and in today's video I want to go over the topic of importance sampling, what it is, why do we use it, and how does it work. And we will see that the word sampling is maybe a little bit confusing, as the importance sampling is not real, it's not yet another way how to obtain samples from some specific distribution, such was the inverse transform sampling or rejection sampling, but it's basically an enhancement for a Monte Carlo integration, which is a very cool topic of its own, and in this video we will get to it what it actually is. So let's get to it. So first, what is Monte Carlo integration? So let's assume that we want to compute the following integral, and if you are given the task of computing this integral, there are several ways you can go. You can use the analytical approach, if it's possible. You can employ some numerical methods such as quadratures or Simpson's integration, whatever, if it's feasible. Or you can leverage the random numbers, the samples, and the laws of probability and statistics. And this is the Monte Carlo approach. And to me, this Monte Carlo approach is it's such a great thing. In this video, I will show you three really great things, but the principle behind Monte Carlo integration is like the first and the greatest thing of all them. So let's get to it. What's the principle behind Monte Carlo integration? So if you recall from statistics, the integral on the left side, it's very much like computing an expectation. Actually, if you replaced, or if we say that the a is equal to minus infinity and the b is equals to plus infinity, it's the exact definition of expected value from the f of x. And if you of course, if we say that this is some probability density function of some distribution. So this is the expected value of f of x under some probability distribution p, and from the law of large numbers we can approximate this expected value, this integral, by average as follows. If we sample from this distribution p and we plug these samples into the function f and we do the average, we will get a really good approximation of the integral on the left side. And this is just awesome. And I love this quote, which says that this is the hammer of statistics, replacing expectations with averages. This is like what statistics is all about. It's just replacing expectations with averages, and suddenly everything works. So this is prime example of how it works in practice, Monte Carlo integration. So let's get to an example actually. So we have this nice integral, and now we want to solve it. Luckily, this integral does have analytical solutions. You can actually use per parts by parts integration, and you will arrive to results of 2. And now, if I want to employ Monte Carlo, I can do it in this way. So let's say, okay, I want to solve this integral using Monte Carlo, and I can say that the x to the power of 2, x squared, is the f of x, and the exponential to minus x is the p of x. And if you recall from probability lessons, the p of x, the e to the power of minus x, is an exact definition of exponential distribution with lambda equals 1, or whatever the Greek letter for the parameter there is the exponential distribution of 1. So basically, I can solve this integral sampling from the exponential distribution, parameter 1, and plugging these samples into this square function and take an average of those to arrive to my results. And now if maybe, I don't know, if the n is equal to 1000 or 10,000, I'm very likely to arrive to a number that's close to 2. And I actually did it, and it's true, so I'm not skimming off the top here. Now maybe Milan, you're asking Milan. So you had this really neat function p of x, and it was this like exponential distribution definition of density function basically. So what if I don't have any p of x that's in the integrand? So what if I just want to integrate a random function f of x? Can I actually use this Monte Carlo thing or not? And the answer is that you can actually use it, because p of x can as well as be probability density function of a uniform distribution. And therefore, if if we like write it down, you have this integral, you can multiply it by 1, and in our case the 1 is b minus a over b minus a, and I can take the b minus a in front of the integral, and now what I am left with is f of x times 1 over b minus a. And by this force of luck, the b minus a is basically a probability density function of a uniform distribution a to b. So you can do it, right? And now if we have this probability density function, we can just employ this averaging, and suddenly if we are sampling from this and we are plugging in here and we have this term here, we can do the averaging and it will be exactly the integral of this function. So this is super powerful tool. This is like the second best thing in this video is basically employing this uniform distribution. That is actually the third one, because the second one is yet to come. But you can definitely approximate whatever function you want using the uniform distribution. So the Monte Carlo integration is super powerful. Now, why do we need the importance sampling? Like what it is? Why do we actually need it? So the Monte Carlo integration has some pitfalls. One of them is that what if I just cannot sample from the desired distribution p? So in the example before, we had this exponential distribution of parameter 1. What if I don't? What if I am not able just simply sample from this distribution? Well, so then I am like bound to not really use the Monte Carlo integration. That's just nonsense, right? So important samplings can deal with this. But also, very nice thing is that importance sampling is commonly used to reduce the variance of the Monte Carlo integration. And what is variance of Monte Carlo integration? It means, let me assume the previous example, is that if I do the Monte Carlo integration, I will arrive the results of 2. But maybe next time when I do exactly the same procedure, I will I will get the result 3, and maybe next time I will get the result 5, and maybe next time I will get the result 1. And now I'm like, what? So am I sure that it's 2, or is it 5, or is it 3, or what's the correct result, or how can I be sure? What I do want to get is much like lower variance of these results. Maybe I want to get something like, okay, so I run it once and it's like this 195. Maybe I run next time it's exactly 2. Maybe I run it again and I will get like this maybe 2.05, and I'm much more confident if I get these results running the integration, Monte Carlo integration 3 times, then I'm getting these results. So here I can say, okay, so it's maybe 2, and here I'm like, wow, so it's 2.5, or is it like 3, or is it like maybe 6, because it's really all over the place. Was I just unlucky? I sampled not the right numbers. So I want really to be sure that the number I'm getting, the result I'm getting, is close to the truth. And importance sampling can actually reduce the variance. It can go from this to this. So that's a very neat thing about importance sampling, is why do we actually use it. And now, the importance sampling, what's it about? And it's this super cool trick. It's like the second best thing in this video. How does it actually work? So here we see the standard Monte Carlo thing, and now let's do the following. So let's just multiply it by, again, this 1 over 1, which actually can be q over q, right? It is still 1, but right now we just multiplied the integrand with q over q, and now the shift happens. So I can actually take this part as my new function I want to integrate, and this q is basically a new distribution I can sample from. So right now I can actually arrive to this formula that this is some function, I don't know, h of x times q of x, and this again is a definition of expected value, but now with respect to q. So it's actually this. I have this q I will take my samples from. This is the probability density function, and then I have this middle term I will be taking the expectation from. And in terms of averages, this is exactly this. So I have my this middle term, and now I'm just sampling from the q. I'm just plugging these samples into this this function, and as I'm averaging it, I'm getting the result of the integrand of the left. And of course I have to be a little bit careful, because the q of x must not be 0 if the top part of the fraction is also not 0, because otherwise I would be dividing by 0, and that's not good. So I have to be a little bit careful, but this is like super cool trick how to shift the expectation from p here to q here, meaning I can now sample not from p of x, but I can sample from the q of x. And this is the trick. And here I just dealt with this third problem, like with this third thirst problem. But what's interesting, and I will get to it in the next slide. So let's wait for it. What's interesting, it also reduce the variance. Before we get to that, there's also another formula how you can basically do the importance sampling, and this formula really demonstrates very nice thing, and that's the probability density functions, the p and q's, do not have to be normalized for importance sampling, because the normalization constants will cancel out. Here is the substitution, like, yeah, so we are assuming that the p over q we will now denote as w, and now if we take this integrand and we will just plug in these the formula right here. Basically this formula is saying that p of x is this is the probability density function, is basically this unnormalized probability density function divided by some normalizing constant. If I plug it in here, I will get this result. And now whatever the normalizing constants are, whether it's alpha here of the w with the wave on top of it, or whether it's beta or whatever gamma, I can just cancel these out, and therefore I don't have to have this w normalized, or the p and q's as written here. I don't have to have them normalized, and I can draw samples from unnormalized distributions and still works fine using this formula. That's cool. All right, so let's go over the important sampling example. We have this familiar exercise. We have this integral, and now we just are bound to not sample from the exponential distribution with lambda equals to 1, but we can only sample from uniform distribution. So we are forbidden to use any other distribution besides uniform. What can we do? We can employ the important sampling, right? So we will just assume that right now we are sampling from this uniform distribution. It's the uniform, let's say from 0 to 10, whatever, and as such it has this probability density function. And now we can just plug it into the formula we saw before. So yeah, so this is the Q, this is the Q, this is the P of X, and this is the F. And basically, if we do this, we will arrive to this average where we will plug samples from the uniform distribution 0 to 10. And if you do this, you will see that the result will be still something about 2, hopefully 2, maybe something around 2. I actually did this. I did this in Python, and I calculated the integral, like the results of the integration, 1,000 times. And always it was number of samples was 10,000, and I just ran these algorithms over and over, then like 100,000 times. And these are the results I get. So when I use the raw Monte Carlo integration using the P as the sampling distribution, which is the exponential distribution with lambda 1, I got this histogram of results. And you can see that most of the times, yeah, it was something about 2, so it was good. It was really nice result. But sometimes I got these like 185, so these 213s, and like if I am super careful about the precision, maybe these numbers are a little bit off, right? So we have this like 0.15, 0.15, 0.13 deviations from the real values. Maybe that's a lot. I'm a little bit more demanding of this, and I want this variance to be much lower. So maybe because it can happen, right? I can run this computation one time, will sample 10,000 samples, and I will get this result, and I say, okay, so the result is 185. Someone will take it, plug it into next process, and suddenly, if I'm using this to estimate, I don't know, length of bridge, the bridge will fall down, and I just made damage for $1 million. So I want to be more precise, and very important, like interesting thing, very important thing is that when I used important sampling using the Q distribution of 0 to 10, uniform distribution from 0 to 10, actually the variance was much lower. I was getting this results around 2, but sometimes I just, yeah, sometimes I got this 195, sometimes I got this 2.05, but the variance was like 0.05, which is much better. It's like 3 times better than this 0.15 on the raw Monte Carlo integration. So how is this possible, right? It's maybe a little bit counterintuitive because here I'm using the P, which was like daring me to use. There was this exponential term in the integral, and I was like, wow, I have to use this. It's P, it's there, it's in the integral. So how does it come that the important sample is giving better results? And on the next slide, hopefully I will give you some intuition why this is happening. So here the black line is our nice function x to the power like x squared times exponential minus x. And if I decompose this function into the two functions, make it so that's the x squared is the green line, and the exponential minus x, this is the blue line, and if I multiply them, I will get the black line. So basically these are the two functions that are making up the black function, my integral function. And now what's happening is that I am basically sampling from the blue distribution. This is what I'm doing. So I'm sampling from this exponential distribution with lambda 1, and what's happening is majority of my samples are somewhere in this region, and that's completely understandable because here is the 1, and we know that the exponential distribution with lambda 1 has the mean of 1 and variance 1. So I can expect that majority of my samples will be in this rectangle. But if you look at the black line, you can see that we are basically like robbing ourselves from all these nice samples on the left side of the rectangle. Yeah, because exponential distribution, yes, maybe if we sample million samples, some samples will be here, maybe a lot of them will be here, but still the majority will be in this rectangle over the left. And we basically don't give a chance to this left, or to the right side, sorry, it's the right side, to even like play game. And the green line here, and I can explain it, it goes really fast up. It has some word in this, and because we are sampling in this rectangle on the left, we are not really giving the space, the opportunity for the green line to really show its force, because here the green line is really low, and if we sample and we plug it into the green line, it's like 0.4, 0.6. That's really interesting. But here, if we plug the fourth in there, it's 16, right? 4 squared is 16, like 6 squared is 36. So the power of the green line is really in these like high numbers, and this is what basically drives the shape of the black line. But we are not really given it a chance because we are sampling on the left. Majority of the samples will be on the left, and the average will be mainly like taken from the samples on the left. If we, however, switch to the uniform distribution, things change. And how does it change? So the blue line, this is the probability density Q, which is like 1/10th, and we are sampling along this line uniformly. So here you can see this blue crosses, this is samples from this line, and we now basically see that these orange dots, these are the important weights. So this is like the P over Q in the axes. And we can say that there these are decreasing because the P of x, this exponential distribution, of course, is decreasing very fast actually. And they are decreasing, but at the same time the green line, like the green dots, are increasing very fast. And even though, for example, in like these dots, the orange is maybe, I don't know, 0, 0, 0 something, the green dots are actually having quite a word. They're quite powerful. So here it's 40. So if I like do this multiplication, I will see that it's not 0, right? It's not 0. It's actually, it has some stake in the averaging. So by sampling uniformly, we are just giving chance to all these green dots here, that in the former, in the raw Monte Carlo integration, they didn't have chance at all. And this makes it like more fair, and therefore the variance, the bias is a little bit lower, and we are getting basically better variance estimates of the integral results. Yeah, and this is a very neat thing to realize that sometimes we are just discriminating things. All right, and this is how we get to these results. So we can see that basically this Q gave more chance to the x squared part of this integral function, and therefore we got a little bit lower variance, whereas here the variance is a little bit higher, as we are not really utilizing the entire x-axis. All right, so selecting the best important sampling function q of x. Here we have 3 points. If you like satisfy them, it's the best q of x we can think of. And the first one is very simple. We have to be sure that we are not dividing by 0. So this is what this bullet is about. Second, we want to be able to sample from qx, because if we are not able to sample from it, it's completely useless. And also we want to be able to evaluate it in all these sampled axes. Again, if we are not able to evaluate it easily, maybe it will be tedious. We will just spend a lot of sampling time and processor time in our notebooks to sample or evaluate just the samples. So we have to be sure that it's easy to sample from and easy to evaluate. And the last thing is very neat. And this comes from the theoretical background. You can check it on Wikipedia, that if the Q is being proportional to absolute value of x times p, it is the best Q we can actually choose. And if Q is directly proportional to p, then the variance becomes 0. So it doesn't matter if I sample 1,000 times, or if I compute the integral once or billion times, it will always get the same answer. This is exactly what you want, because this is what saves times. All right, so now quiz, and you can pause the video if you want. But basically, the quiz is what of these 4 options of q of x, this red part of the pictures, is the best. What is the best sampling distribution? And maybe now pause the video, think about it, and we will get to it. So let's get to it. If we go one by one, so the first one is definitely the first one. We are sampling a lot in this region, right? It's a high probability here, and unfortunately, most or all of these samples, if we plug it into this formula, it will be 0, because if we can see that the black line is terminating on the left tail of the Q function, and then 0. So we are sampling like crazy. We're sampling millions of samples, and most of them are not being used at all. And we are not really evaluating the integral at all. So this is not a good choice of q of x. And if we actually go for this, we will burn a lot of computational power. Nothing will happen, and it will be very not good. Second picture, it's much better than the first one. So I'm not talking about this picture, but we can still see that there is lots of these samples that are not being utilized at all. So we are again sampling like crazy. All these samples are good. We are evaluating the integral there, but most of them on the tails especially are useless. So we are like burning a lot of processor time to sample these, and they are useless, unfortunate. All right, then we have the third picture, and this is actually very good. We are sampling from this uniform distribution. It's good. We are utilizing most of the samples, so that's actually a pretty good distribution to sample from. But by far the best one is this fourth one, and this is because the q of proportional to the f and P of x's, and therefore most of the samples we get here, basically all of them, are being utilized very well in the importance sampling integration algorithm. So this is the one we would like to choose. This is like zero samples wasted in terms of computational power, and also we will get very fast to the correct results of the integrand. All right, so that's it. Some concluding notes. So the goodies. Importance sampling can be employed in the settings where we don't have like the proper sample from P of x, or we are just not able to sample from P of x, or it's tedious to do it. We can employ importance sampling, and we can use this Q of x sampler instead of the P of x. Again, very nice thing is that we can actually perform quite well in higher dimensions to compare, for example, to numerical integrators. It's just like the property of Monte Carlo integration methods that they are quite good in the higher dimensions, and it's not so tedious as the numerical integrators. And the last but not least is if we choose the Q of x, the importance sampling distribution, well, we can lower the variance compared to the raw Monte Carlo integration. So that's the good things. Now, what you should take care of, or what are the points that are quite tricky. So first, choosing the right importance sampling distribution is a little bit of art. It's like it's not so easy. You have to, in the practice, you have to maybe try few sampling distributions out there, and you will have to see which one performs the best. There are like entire papers written on how this can be achieved. So it's a little bit neat thing, and we saw it in the previous slide that if I choose wrong importance sampling distribution Q, I will just be completely thrown away, and if I choose the right one, it's very efficient distribution to proceed with. And then last but not least is the tails of the distribution matters node. And to demonstrate this, let's assume like the picture down here. If I sample some x from the Q of x, and the Q of x does have a little bit not so heavy tails, and I plug it into the fraction right here, I can see that if the x is maybe on the right side of the tail of the Q of x, then the Q of x actually in this point will be very low. It will be close to 0. And again, if I am if the f of x times p of x is not close to 0, it has heavier tails, then this fraction will tend to go to infinity. And even maybe it's just one point I sampled in this very like right tail distribution. Maybe majority of the samples were somewhere in this region. But if I just sample this one bed fluid here, and I do the summation, and I sum somewhere something close to infinity, it will just throw off my entire estimation. So I have to be really cautious about it. And preferably, I don't really want to have this Q distribution have much lighter tails, or this f of x times p of x much heavier tails compared to the other one. All right, so this is it. Hopefully it was useful to you guys. Here are some good sources you can maybe follow up from this video. I will put them into the description of the video, so you can easily click on them. And if you have any questions, please comment on this video. If you liked it, please give it a like, and hopefully next time. So cheers.